12, we're going to make a video here looking at some, well, I've called it chemical sleuthing, but it's using multiple spectroscopy techniques to identify an unknown molecule. Okay, so here I've just given on this first page a brief outline. First you need to, if you've given a formula, a molecular formula to calculate the degree of unsaturation, and think about some possible structures from that. A molecular formula can give you a lot of information. So in this first section of problems, I've given you a molecular formula to help you out. And I've also given you an IR spectrum for the molecule and then some NMR, haven't I? Oh, yeah. Okay, so part one, I've given you, for each one, a formula, an IR spectrum. Hopefully you can recognize that. And also a proton NMR spectrum, okay? I can tell it's telling me hydrogens, and also this chemical shift is really small. Remember, the chemical shift on carbons ends up being much larger, okay? So for the first set, each page is just dealing with one molecule. I've given you a molecular formula, an IR spectrum, and a proton NMR, and there is several of those, but we're only going to do a couple of them together. And then part two, no molecular formula, but we have a mass spectrum, an IR spectrum, and then we have carbon NMR, carbon-13 NMR, and proton NMR to help you identify the molecule. All right, I put little asterisk scribbles around the ones that I'm going to work through, so let's get started together. All right, so this molecule here has the formula. Before I even look at the spectrum, it has the formula C5H10O. Okay, there are analytical methods where you can just get the molecular formula, but we don't really study those, so let's just take it for granted that we know the formula. Okay, just looking at the formula, does it fit the 2n plus 2 rule? Are we dealing with an alkane backbone or an alkane backbone? But we've got an oxygen in here too, and so the main ways that we know oxygen can bond and combine is we could have an alcohol here, or we could have a double bonded oxygen, so like a aldehyde or a ketone or something like that. But let's think about it. Ignoring the oxygen, C5H10 doesn't fit the 2n plus 2 rule. It just fits the 2n where n is 5, so H10. So it means that we haven't got an alcohol, okay? And we don't have an alcohol, we could have an alcohol, but we've got a double bond in there, okay? But we don't have an alkanol. I should erase that. We don't have an alkane backbone with an alcohol group of it. Alkanol, okay? If it did, it will still fit the CnH2n plus 2 O rule, okay? Because if you think about it, an alcoholic oxygen doesn't take the space of a hydrogen, it just kind of pushes it out one. Maybe I should draw that, okay? It just takes the space of a hydrogen there. It just pushes it out further from that. It doesn't take the place of it if it's an alkanol, okay? So we've got a double bond in this molecule, okay, because it fits the 2H2N rule. It could be a carbon with an oxygen double bonded, or it could be a carbon-carbon double bonded, but you know, you can't do double bonds with a hydrogen. So we could have an alkene backbone there, or we could have a carbonyl, okay? Carbon double bonded with oxygen, okay? We could have a straight chain backbone, we don't know, but we could have an alcohol on an alkene, or we could have an alkane backbone with a carbonyl there, okay? We've got 1 degree of unsaturation. All right, so from there we can't tell too much. We can look at our spectra here and see what we've got. Okay, so remember this, trying to highlight, this area of the spectrum is not telling us much, but the thing that jumps out to me here is this deep peak here. Okay, remember when we're looking at IR spectra in our course, nice and simple, we're looking at this region and this region, okay? And it's telling us if we've got any oxygens bonded here. And here it's saying, you don't have an alcohol. Remember the alcohols will produce those deep peaks there. Sorry, the wide ones too. And the 1700 to 1750 range, a deep peak like exactly as shown here, is saying, hello, you've got a carbonyl, okay? So that's the evidence that we've got a carbonyl molecule here. Okay, so we can go back to our original formula and go, we haven't got an alkene backbone. We're dealing with an alkane with a carbonyl in there, okay? So if we're dealing with an alkane backbone with a carbonyl in there, we have either got the carbonyl on the end of the molecule, so it's an aldehyde, or it's in the middle, so we've got a ketone is the word I'm looking for, okay? We can't get any info any more info other than it's not an alcohol, okay? So we've got a carbonyl there. That's all we can get from the IR spectrum. Let's look at the proton, okay? Now let's make sure we've got 10 hydrogens in our formula. Now look, they've given the integration for us. 2, 5, 7, 10. Okay, all the hydrogens are accounted for. How many peaks are there? There are 4 hydrogen regions there, okay? 4 hydrogen regions, or environments, I should say, 4 hydrogen environments, okay? That's telling us a lot already, and you could probably work it out in the long term, but 4 hydrogen regions on 5 carbons says that one of the carbons doesn't have any hydrogens attached to it. Now, as I said earlier, the carbonyls are either on the end as an aldehyde or in the middle as a ketone. Okay? If this was an aldehyde, all of the carbons would have hydrogen environments associated with them. Okay? You'd have a hydrogen environment of 1, or you'd have, a hydrogen environment with an integration of 1 for an aldehyde as well. We've got 4 hydrogen environments, suggests that one of the carbons does not have a hydrogen environment. Good. Ketone. And also we do not have a hydrogen, 1 hydrogen by itself there in there as well. So we have not got an aldehyde, okay? So I'm going to put a big cross there. So we've got some form of ketone, okay? A ketone on a pentane backbone, or maybe shorter with branches, we don't know, but let's see, okay? What I'm going to do is I'm going to draw some possible isomers here and see what fits, okay? So 1, 2, 3, 4, 5, okay? We could have this ketone, or we could have this ketone if it's a straight chain, okay? We haven't established that it's a straight chain yet, but we can check it, okay? It could have branches, all right? Should we draw them in anyway? Okay, 1, 2, 3. Well, we can't put a branch on that second carbon, but we could go 4, 5. I think that's the only other option that we could have there. All right. Let's put our hydrogens in there, and let's see what's fitting. 1, 2, 3 there. No more can go on that second one of this one. 1, 2. I know it's getting a bit squashy. 1, 2. 1, 2, 3. Okay. Let's put them in. Oh, I shouldn't have drawn them this squashy. It's making it harder to see. Alright, and what we're going to do for each of these potentials is look at how many hydrogen environments they are. I know a few of you might have gotten there already, nice and quick, but we'll take it slow. And my writing is so squashy, apologies for that. I might get out the highlighter, and I'm going to highlight hydrogen environments. Okay, maybe I should go for yellow. So on this first one here, you can see that oxygen's in the middle. Okay, it's making the molecule non-symmetrical. Okay, so these three, well, I wanted the highlighter with yellow. These three hydrogens are in one environment, and then these two are in another environment. Okay, they're not equivalent to anything else. Then these two are in their own hydrogen environment, and then these three on the end. So we should see 4 hydrogen environments with this molecule with integration 3, 2, 2, 3. That's what we're seeing here, 3, 2, 2, 3, okay? Let's just make sure with the further down molecule, okay? So the one in the middle is very symmetrical, okay? And so these two CH2s will be in the same environment. You can interchange those and not change the molecule. So that's just one environment. And then these methyl groups on the end, sorry, I'm not using the highlighter. These methyl groups on the end are also interchangeable. So that molecule there only has 2 hydrogen environments. So let's put a scribble through that one. Wrong, because only 2 H environments. You'd only have 2 peaks there. Okay, let's check this last one. So this one will be a hydrogen environment with 3. Down here we'd have a hydrogen environment with 1. Okay, we're already on a problem. We don't have an integration of 1 there. Okay, and look down here. This methyl group and this methyl group, you could exchange any hydrogen there. So we should have, they'd be in the same hydrogen environment. So for if it was this bottom molecule, we'd only have 3 peaks with an integration of 3, 1, and 6, and we don't have that as well. So cross that out as well. So the only option that we have is this one here up the top, and let's just check with our multiplicity and our positioning here to make sure that we have got it right. Okay, so and we can assign which peak goes to which one. I'm going to use green here, I don't know why. Okay, so we've got 3 hydrogens that have 0 neighbours, okay, on the carbon next to it. Here we have 3 hydrogens in a singlet and the n+1 rule, 0 plus 1 equals 1. So this relates to this one here, okay? So that peak there. It's also downfield because it's close to the more electronegative atom there, which is the oxygen, okay? Swap colours. I know it's getting a colourful mess here. Okay, our next one, our hydrogen environment with 2 hydrogens here. How many neighbours does it have? Well, it just has these 2 to the right there in the pink there. So we need 2 hydrogens with 2 neighbours. So it's going to be 2 hydrogens in a triplet, n+1 rule. It's going to be downfield because it's near the oxygen. Yep, that's right. It's this one here. Okay. Orange. This one here. 2 hydrogens with how many neighbours? Okay. 1, 2 to the left and 3 to the right. So 5 neighbours. So it should be in 6 peaks. Okay, 2 hydrogens, 1, 2, 3, 4, 5, 6 peaks. It's this one here. And it is kind of getting slightly further away from the more electronegative atoms. So it's slightly downfield, okay? Words. The methyl group up the end. Oh, I just erased some stuff, but that's okay. The methyl group down the end, we've got 3 hydrogens. That's promising with this one. How many neighbours? 2 to the left there in the orange one. So we should have a triplet, n+1. So that one's here, and we know it's also fitting with its chemical shift, that it's the furthest upfield because it's the furthest away from the electronegative atom. Okay, so our actual answer Let's redraw the molecule again. We've got a CH3 on the end, and then a carbonyl on the second, and then a CH2, CH2, CH3. What's this one called? It is 1, 2, 3, 4, 5. Pent, not pant, P-E-N-T. It's alkane backbone, so a pentan, and it's an one, but I'm going to leave a space because we saw that there was a positional isomer there. In the 3 position, here we must have the 2 position, pentan 2 one. Okay, it's not the pentan 3 one, pentan 2 one. All right. I'm not going to do number 2. Give it a try for yourself. Oh, I've put an asterisk next to number 3. Okay. Oh, look. C4H10O. Didn't we have C5H10O? We had C5H10O. C4H10O. Okay. 2n plus 2 rule. Does it fit? 2 times 4 is 8, plus 2 is 10. So it fits the 2n plus 2 rule. Let me get my pencil back. 2n plus 2 rule. So it's an alkane backbone, but it has an oxygen in there too, okay? And the only molecules that we've studied so far that have an alkane backbone with an oxygen in there is an alcohol. So it must be an alcohol. Helps if I could spell it. Alcohol. Or we could say an alkane that has an alcohol group is sometimes called an alkanol. It tells us that we've got an alcohol group and we've got a saturated backbone. Words. Okay. All right. So there's a few isomers that we could have here, but let's just make sure and confirm that we have got an alcohol from our infrared spectrum. These are the 2 regions that we're looking for. Okay. Have we got a carbonyl peak? No carbonyl. We've got a nice wide one there around 3400. That's telling us that we've got an alcohol. It's not the widest that you've seen. You get a wider one with the carboxylic acid, but you also get that carbonyl there too. So it's confirming that we do have an alcohol. Okay, the IR spectrum saying, hey, you've got an alcohol. So we've got an alkane backbone C4H10O. Here's our proton NMR, but let's draw a few structures. 1, 2, 3, 4. Okay, 1, 2, 3, 4. We could have alcohol on 1, alcohol on 2, alcohol on 3 or 4 would just be the 1 on the 2. Okay, so they're the positional isomers of the butane backbone. Let's take the backbone down by 1 and put a methyl group. Well, the only methyl group you can put on this propyl is in the 2 positions. So we've got a methyl propane. Okay, there's a couple of places where you can put the alcohol here. I'm getting a bit ahead of myself. Okay, we can either put the alcohol on one of these methyl groups coming off it, or we could put it on the middle one there. So I've got 4 possible isomers there, and I might just put my hydrogens in because it'll help us. Okay, with the proton NMR. Okay, so I will have 2 more hydrogens coming off there. 1, and this will have 3, and this will have 3. Okay, I've got that one there, that alcoholic hydrogen, and I will have 1, 2, 3. 1, 2, 3. 1, 2, 3. And back over to these straight chain ones, I'll have 1, 2, 1, 2, 1, 2, and 1, 2. Okay, because this molecule has an even number of carbons in its backbone, well, it could if it was straight chained, it's not allowing for a lot of symmetry, where you get less hydrogen environments. You get some repeating hydrogen environments. So that's kind of helping us out here. So, I might change colour. How many hydrogen environments do we have in each one? Oh, I forgot a hydrogen on there, didn't I? What a duffer. Okay, we have got 1, 2, 3, 4, 5. Okay, so that's 5. Okay, the one below, 1, 2, 3, 4, 5. Okay, so 5 for each of those. Here we've got 1, 2, 3, 4, 5. And the last isomer we've got, 1, 2. Have I done that correctly? 2 hydrogen environments. Alright. Let me just check with my working. Have I done all the possible isomers? Maybe I've missed one. Have I missed an isomer? I'm a bit paranoid because look, we've got 1, 2, 3, 4 hydrogen environments, and each of them have. I think I've missed an isomer. Let me just check. Look, from the proton end, I've got 1, 2, 3, 4 peaks, and I shouldn't have 4 peaks. 1, 2, 3, 4, 5. Sorry about this pause. Am I counting? You're probably yelling right at me. It's that one! What are you doing? Oh, I know what I've done wrong. Look at this one. What a duffer. Okay, on to this one. Sorry, here. 1. Those two can be interchanged. 3. And look, from there, the methyl groups are symmetrical. So they are just the same hydrogen environment. I'll smear it across. 4. Oh, I did have the right. I didn't miss one. I just couldn't count my hydrogen environments the same. Okay, 4. So that's really helpful because we've got 4 peaks on the top one. Let's just make 100% sure that we've got the right one, okay? And let's assign a peak to each hydrogen. Now, let's start with the alcoholic hydrogen. Remember, there's a funny rule with that one. Okay, it's 1 hydrogen in its environment, so we've only got 2 of those. And it's also the closest to the more electronegative atom, okay? So I'm going to assign it to this one. Notice it's a singlet. How many neighbours does it have? Well, it actually has 2 neighbours, but remember that funny alcohol rule where an alcoholic hydrogen doesn't see its neighbours? Okay, I'm still sure it's that one down there. Furthest downfield, 1 hydrogen, okay? It won't see its neighbours. Remember, those alcoholic hydrogens don't see their neighbours. All right, coming across now, you can see that the ones on this carbon here, the 2 of them, well, there's only one with an integration of 2, and it's further downfield. How many neighbors does it have? Okay, it won't see the alcoholic hydrogen. It sees the hydrogen over here, further along, so it's just going to be a doublet. Okay, so that's that one there. Okay, and it's also second closest to the oxygen. So coming along now, further upfield, we should have one hydrogen. That's good. And look at how many peaks we've got. Okay, it's got a lot of neighbors. That's okay. Let's count these peaks. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right. Let's just make sure. 1, 2, 3, 4, 5, 6. The two methyl groups. 7, 8. Is it seeing that one slightly? I'm still happy with that. Okay. I'm still happy with that splitting. It's one hydrogen with a lot of neighbors. Okay. This last one here. Let's do it in this dark blue. Okay. We've got 6 hydrogens. That's good. Oh. I don't want my eraser. I want my 6 hydrogens. And they'll only see one neighbor, so it should be 6 hydrogens in a doublet, which it is. So that's that one there. All right. So it's this molecule here, which I might redraw. So it had this backbone, and it had the alcohol off there. All right. So I'm going to call this the backbone. The alcohol would get the smallest number, but it doesn't really matter because the methyl group can only go in one place. So it's an alcohol at the end. So it's an ol. Okay, remember with that backbone we could have put the alcohol in the second position, so we're going to need a number. So it's a 1-ol because we'll give it the lowest number. So that carbon number 1 is the one on the left. It's a propan, because it's 3 carbons in the backbone, and the thing that's coming off is a methyl group there. The methyl group can only go in the 2 position. It can't go in 1 or 3 because then it won't be a propanol, so we don't need to number it, and we shouldn't number it. Okay, it's a redundant number. It's a methyl propan 1-ol. Okay, we need the 1 for the ol because it could be methyl propan 2-ol, which is this one that we drew just below. Okay, so we've identified it to be methyl propan 1-ol. Let's keep going. Number 5 here. Okay, C3H6O2. Ooh, we've got two oxygens here. All right. It's fitting the 2n rule. So we must have... we could have a cyclo, but let's not do cyclo. It's not. Very unlikely. Not steric hindrance, ring strain. So let's just presume that we've got a double bond in there, okay? So we've got a double bond in there. It could be a carbon double bond, but since we've got 2 oxygens, I'm leaning on there's a higher probability that we've got a carbonyl in here, but we can't really tell. Let's just jump down to the IR spectrum and have a look and see what it's telling us. Look at these regions here. Okay, not only do we have a carbonyl, so that takes care of that potential double bond, we've also got this really wide alcohol peak. And the carbonyl, when it's right next to the alcohol, makes that really wide carbonyl peak, or it's saying between the 2 of them, or even just the one of them, but especially between the 2 of them, hello, you've got a carboxylic acid. Okay. So that is classic carboxylic acid from the IR spectrum. Okay, so we've got a carboxylic acid. It's taking care of that double bond, so we must not have anything else happening there. It's taking care of the 2 oxygens. So we've got 3 carbons with a carboxylic acid. So let's see what isomers we can do. There's pretty much not much we can do, but let's make sure. Let's put a carboxylic head there, carbon there. Now, we can't put a carbon on the first one. We need to put the extra carbon there, okay? There's no other way you can go. That's taking care of the 3 carbons. There must be... Oh, sorry about that. There must be hydrogens there. There's no other isomers that it could be apart from this one, propanoic acid, okay? It must be propanoic acid, but let's just check the proton NMR just to make sure. How many hydrogen environments do we have? Can't talk. 1. And then these 2. And then the methyl groups at the end. So we should have 3 peaks. Have we got 3 peaks? Yep. Okay. The green one should be furthest downfield and has no neighbours. There we go. So it's a singlet. It's a very mild singlet too. They've had to expand it out. Coming along upfield, we've got 2 hydrogens, and it is a quartet. 1, 2, 3, 4. So it must have 3 neighbours. That it does. There's 3 of those red ones there. Okay. And then red must be this one here. It's a triplet, so it must see 2 neighbours. Yep. So we've confirmed it. So that's a nice easy one. It's propanoic acid. Alright. Let's keep going. You can do that one for yourself. Here's the harder ones. No molecular formula. But we have a mass spectrum, and we have a carbon-13 NMR here. Okay? So if these... There's multiple ways where you could start. But for this first one, I might start down and look at how many hydrogen environments we have and how many carbon environments we have. Okay? Although, there's multiple places where you can start. Okay? I'm seeing this right in the middle of my page. And it's screaming out to me. So it doesn't really matter, but look. That's a carbonyl peak. Okay? So we've got a carbonyl there. Okay, let's finish off the IR spectrum. What's it lacking there? It's not an alcohol. There's no alcohol group, but we've got a carbonyl. So we could have an aldehyde or it could have a ketone. Okay, the carbonyl group could be end. It could be in the middle somewhere. Okay, so we must have at least an oxygen in there. Okay, and we must have some carbon in there too. Okay, all right. Let's look. So here's our carbon-13 NMR, and I can tell that because it hasn't got any splitting of the peaks, and it's got high ppm numbers, okay? Less information because carbon-13 is less abundant than hydrogen-1, okay? How many carbon environments do we have? 1, 2, 3, 4. So there must be 4 carbon environments. Or, another way to think of it, must be at least 4 carbons, okay? Now, let's have a look at the proton NMR. Okay, we have 1, 2, 3 peaks, okay? So we've got 3 hydrogen environments, and there's an integration here, okay? We have actually got 8 hydrogens, okay? The safest thing to do here is to presume that you only have 4 carbons for the environment and you've got 8 hydrogens and you've got the 1 oxygen. See what mass you come to and check that against the mass spectrum. Okay, so 1 oxygen, 4 carbons at least. We could have more. We could have overlapping environments, but let's just see. And we've got 8 hydrogens. Okay, so we could, the smallest kind of molecular formula we could have from that information is C4H8O. Let's work out a mass for that. 4 times 12 plus 8 times 1 plus the 16, and let's see what we get, where we should see our top parent peak in our mass spectrum. 4 times 12 plus 8 plus 16 gives us 72 gram per mole molecule. look at this parent here, 72. Okay, so the mass spectrum is confirming that what we assume to be our lowest is actually our molecular formula there, C4H8O. Okay, and we know it's a carbonyl, so we need to decide, is it a straight chain? Has it got a branch in there? Is it an aldehyde or is it a ketone? Okay, let's keep going. All right, should we draw out our possible structures? 3, 4. Okay, we could have that one. 1, 2, 3, 4. We could have this one. All right, let's shorten it. Okay, shorten it to 3, and you'll have to put a methyl branch on that middle one, and you can't because it's got 4 bonds already. So it can't have a propane backbone. It must have a butane backbone. So it must either be the top one, or it must either be the aldehyde or the ketone of the straight chain butane backbone. Okay, so let's draw our hydrogens in here and see how many hydrogen environments we get. Yeah, let's do it. Okay, well, let's just make a start. Okay, hydrogen, 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 hydrogen. So if it's this one here, we should see an integration of 1, 2, 2, 1, 2, 2, 3. No, we haven't got 4 hydrogen environments. Okay, and we've got 2, 2, 3. All right. It's kind of like the problem we did earlier. 3, there's no hydrogens on that second one. A 2, and then a 3. We've got 3 hydrogen environments for this one. And it's 3, 2, 3 integration. We have our culprit. So it's this one here, which is known as, it's 4, so it's bute. And it's a butanone. We don't need to put a number on where our ketone is, our carbonyl is, because it can only go in the 2 positions. So we just name it as butanone. Okay. All right. I'll leave you to do problem 8, problem 9, and let's look at the last problem in the set. Okay. I'm going to start with IR. Look, it's missing something, and it's missing something. Okay? Oh, writing in yellow. Sorry. No oxygens. Okay? Not alcohol or not ketone or anything like that. So we don't need to worry about that. Okay? Also, it's got an awfully large mass. Okay? One thing could be staring you here too. Look at that little double peak that's 2 away too. See if that rings a bell. Okay? I'm going to go down further here, but I'll come back to that. Okay? How many carbon environments do we have? 3. We've got 3 peaks, okay? So at least we've got 3 carbons in there. Okay? We could have a lot more, and especially fit since we've got a mass of 125. But hold on. How many hydrogen environments do we have? 3. And we've got an integration of 2, 2, 3. So we've got 7 hydrogens. So we must only have 7 hydrogens in here. 7 hydrogens on an organic molecule that has a mass of 125. What is going on? Alarm bells should be ringing. Okay? Alarm bells should be ringing. How did it get this huge of a mass? Okay? You may remember back. And this double peak 1-to-1 at 124 and 122 may help you out, okay? Also, what may help you out is this jump. Look at this big mass drop there for those fragments. There's a drop there That's going from about 124 down to like 48 or something like that. 124 minus 48 is giving us 76. That's a huge mass drop. What has dropped off there? All right. Hopefully you've got to the point where you're thinking of those isotopes. Yeah? This is bromine. 1 to 1, where there's 2 difference, is a bromine peak. Okay? And it's hinting that the mass, because if we look at the mass of bromine, it's a large one, so it's about 80. Oh, so the two ones are on there. Whoa, I don't remember what they are. Is it 81 and 79? Let's Google that. But I'm still very happy that it's bromine. So if I Google bromine and I look up at its main ones, I'm trying to remember its main masses. It's got 2 isotopes, 79 and 81. Okay, so it's 79 and 81. Okay, so that's what's taking into account there, and that's why it's got such a huge mass. Okay, so we know it's got a bromine in there. We know it's got 7 hydrogens, and we know it's got at least 3 carbons. So let's try carbon 3, C3H7Br. Okay, let's try that, and let's see if it goes up to 124. Okay, what mass are we going to use for? We'll use 80 for bromine. Okay. Oh no, we'll use the 81 and see if it gets to the 124. So 81 plus 7 plus 3 times 12, 124. Hello, we've got our formula, C3H7Br. Okay. Remember, when we're looking for unsaturation in possible structures, or if we have double bonds in there, that we count halogens as acting like hydrogens. So let's think about C3H8. That fits the 2n plus 2 rule. So it's saying we've got an alkane backbone with bromine on there. Let me change colours and we'll draw possible isomers. 1, 2, 3. Okay. We could have bromine on the 1, or we could have 1, 2, 3 bromine on the 2. Can we shorten it? No, we can't shorten the backbone and then put a methyl group on there. So these are our 2 isomers. We could have 1 bromo propane or 2 bromo propane. Okay. Now what we're going to have to check out there is the splitting in the the proton NMR. Okay, let's draw our hydrogens in there. All right, 2, 2, 3, 2, 2, 3. Let's just make sure this other one would have 3, 1, 2. So it's not this symmetrical one here. It wouldn't have 3, 1. Sorry, 3, 1, 3. It would have 6 and then 1. It would only have 2 hydrogen environments. So it's this one up here. It's 1 bromopropane. 1 bromo with an O propane. Okay. All right. Hopefully me working through those problems have helped you out. Give the other ones a try.